And welcome back, and let's talk about applications of all that we've seen so far to cryptography with the concept of finding multiplicative inverses modulo n. So let's suppose that Alice and Bob are trying to communicate with each other, and they're using an affine cipher with a key of 11-2. And let's remind ourselves what we mean by that. And let's suppose Alice is going to encrypt the letter G. Now, the letter G, we're first of all, in an affine cipher, going to convert this into a number according to its position in the alphabet. And G, if you start with A equals 0, you'll end up with G equaling 6. Now, with this particular key of 11 and 2, what Alice is going to do now is compute 11 times 6 plus 2 mod 26. And then that will be a number between 0 and 25. Let's see what number that is. Well, 11 times 6 plus 2, of course, is 68. And 68 mod 26, we get that by taking 68, dividing by 6, and keeping the remainder. That is a 16, which is going to encrypt to the letter Q if you count through the alphabet. So using this affine cipher, Alice has encrypted the letter G to be the letter Q, and that gets sent to Bob. Now, what does Bob have to do? Well, Bob is going to take the letter Q and kind of reverse the process. And it's in this reversal of the process that we're going to see the application of the Euclidean algorithm and extended Euclidean algorithm. Bob has received the letter Q in the mail or an email, and he's going to convert that into a number 16 according to its position in the alphabet. Now, Bob also has possession of the key, which is 11-2. Now, what Bob has to do is work backwards. He needs to find the plain text. He needs to find the x such that 11 times x plus 2 would equal 16. So Alice has gone through the process. She knew the x and ran it through this process forwards. Bob, on the other hand, knows this and has to work backwards to find the x. Now, how would we do that? Well, this has an equal sign in it, right, in this equation here, but it's not truly an equals because it's a modular arithmetic equation. It's a congruence equation. So we can do a few things, but we're going to have to think of some different kinds of mathematical steps here in just a moment. One thing we can certainly do is subtract 2. Subtraction is a perfectly normal modular arithmetic process, and this is going to leave us with 11x equals 14 mod 26. Now, Bob needs to solve for x and figure out what that plaintext character was. If this were just 11x equals 14 for a moment, let's just pretend that's not even here. If this were just 11x equals 14, this would be really simple. We would just say x is equal to 1 over 11 times 14. However, this isn't regular arithmetic, this is modular arithmetic, and so I don't really know what a fraction is in modular arithmetic. In modular arithmetic, the only things that are allowed are integers. So I don't really know what this is. Okay. Another way we often write fractions is with a -1 exponent. So I'm going to write that as 11 to the -1 times 14 mod 26. Now, what is this thing that I've just written down, 11 to the -1? This is an integer. Let's call it b. It's an integer called b such that 11 times b is equal to 1 mod 26. If this were ordinary number arithmetic where anything goes, fractions, decimals, everything else, and I could just write 1/11th and be done with it because 1/11th is this unique number such that when you multiply it times 11, you get 1 back. But if I'm going to be doing arithmetic mod 26, then this b right here needs to be an integer that's between 0 and 25. So what is it? Well, here's where I'm going to take a short break here and talk about the general idea. Okay, so what we're working with here are ways to undo multiplication. When we divide by a number, we're trying to undo a multiplication step. This is easy to do when you can use any sort of number you want, but when you're only restricted to integers, it's not so easy. So we're going to make a definition here. We're going to say that the multiplicative inverse of an integer mod n is the integer y such that x times y is equal to 1 mod n. For example, in the previous problem here, I'm trying to compute the multiplicative inverse of 11 mod 26. I'm looking for a number such that when I multiply it times 11, I get 1 mod 26. We're going to use this notation of x to the minus 1 power to indicate this number, but remember that's not a fraction, that's another integer. Okay, some examples here, 5 to the negative 1, or the multiplicative inverse of 5 mod 7 is 3, and that's because if I take 5 and multiply it to 3, I ordinarily get 15, but that's equal to 1 mod 7. So 5 times 3 is equal to 1 mod 7. Likewise, the multiplicative inverse of 3 mod 8 is 3 itself, and that's because 3 times 3, ordinarily that's 9, but that is equal to 1 mod 8. So 3 times 3 is 1 mod 8. So now back to the story. We're trying to find the multiplicative inverse of 11 mod 26. So I'm trying to find a number b such that 11 times b is congruent to 1 mod 26. This would be easy enough to do just by checking or guessing and checking, just by trying numbers starting with 1, then 2, then 3, then 4, and just continually plug them in for b and see what we are going to get. But there's a process here that I want to illustrate using the Euclidean algorithm that is a little more foolproof. So we're going to actually use the extended Euclidean algorithm to find multiplicative inverses. So we're going to now use this to find the multiplicative inverse of 11 mod 26. So we're going to use the extended Euclidean algorithm. Let's start by using the Euclidean algorithm to find the GCD of 11 and 26. Now, you can probably just look at these two numbers, 11 and 26, and know that the GCD is going to be 1. These are relatively prime integers. And in fact, in the affine cipher, I think we all understand that we can only use multiplication keys that are relatively prime to 26. This is one of our big concepts from the course. So I know the GCD is going to be 1, but let me work through the Euclidean algorithm anyway just to see the steps. So the Euclidean algorithm would say to compute the GCD of 11 and 26, I'd start by dividing 26 by 11. That is going to go in twice with a remainder of 4. Now, I haven't hit a 0 remainder yet, so let me shift and divide 11 by 4. And I can see pretty easily that goes twice with a remainder of 3. The remainder is still non-zero, so I'll keep going, shift and divide 4 by 3. That goes in once with a remainder of 1. And in the next step, I'm going to take 3 and divide it by 1 and have a remainder of 0. So let me draw a little line right here, and there's my GCD. Now, let me use the extended Euclidean algorithm to go backwards this direction through the process. I'm going to start by writing 1 equal to 4 plus 3 times negative 1. In other words, subtract, go to the next to last equation, this guy right here, and subtract 3 from both sides. Now, the 3 is right here as well, and I can make a substitution here. The 3, I'm going to substitute, this is all being multiplied by negative 1, is equal to 11 plus 4 times negative 2. So if I distributed the negative 1 through here, I would end up with, there's a 4 out in front here, and I have 4 times negative 2 times negative 1. This is 4 times 3 in all. And then the negative 1 also distributes to the 11, and so I have this. Now the 4 is this remainder, and I can solve for it as well. Let me make that substitution. So 4 can be written as 26 plus 11 times negative 2. This 4 was being multiplied by a 3, and I'm adding on 11 plus negative 1. So in the end, when I do all this distribution, I end up with a 26 times 3, and check that this is 11 plus, or times negative 7. Okay, and this is all equal to 1. So just like we said in the previous videos, the GCD is equal to 1, and I can always write that GCD as a linear combination of the numbers that gave me the GCD in the first place, 26 and 11. Now I want to pay particular attention to that equation that I wrote right here. I'm just going to go and put this on another slide. Here we go. So I just discovered that 1 is equal to 26 times 3 plus 11 times negative 7. Now that's an ordinary integer equation. What happens if I reduce both sides of this equation mod 26? So I'm going to look at both sides of the equation and reduce them mod 26. That is, I'm going to divide each of the, or all of the numbers here by 26 and keep the remainder. If I divide 1 by 26, that goes 0 times, and I have a remainder of 1. Now, if I take 26 times 3 and divide by 26, what's going to happen? Well, obviously it's going to go 3 times and have a remainder of 0. So 26 times 3 mod 26 is actually 0. And then this is going to be 11 times negative 7. I'm actually not going to work that out. What I want to illustrate here is if I take the equation that resulted from the extended Euclidean algorithm and reduce both sides mod 26, what I've discovered here is that 1 is equal to 11 times negative 7 mod 26. And this is a partial answer to the question I had just a couple of slides before. What do I multiply 11 by to give me 1 mod 26? Apparently it's negative 7. So that is the multiplicative, that is at least a multiplicative inverse for 11. 11 times negative 7 is congruent to 1 mod 26. The one other thing I'd like to do is negative 7 doesn't correspond to a position in the alphabet. So I'm going to take negative 7 and reduce it mod 26. Negative 7 is the same thing as 19 mod 26. So what I've done now is I've found what I was looking for. I now see that 11 times 19 is equal to 209, and 209 mod 26, you can check for yourself, is 1. So if I'm looking for the number such that 11 times whatever is equal to 1 mod 26, that number is 19. And so we're going to write that 11 to the negative 1 power is equal to 19 mod 26. That's the multiplicative inverse of 11. And how I got that, again, just to recap, was by starting with the Euclidean algorithm, finding the GCD, and then working my way backwards using the extended Euclidean algorithm, and then reducing the result of that extended Euclidean algorithm, mod 26, and then shifting forward in the alphabet to find a number that's in the right frame of reference, which would be 19 at this point. Now let's get back to Bob. What is Bob going to do? What was Bob trying to do? He was trying to find a number such that 11 times that number is congruent to 1 mod 26, and that number is 19. So in order to get the plain text back, to get the x, he's got to take 19 times 14 and reduce the result mod 26. Let's do that right here and see what happens. So 19 times 14, that, using your calculator, is equal to 266. If we reduce this mod 26, take that and divide by 26, that's going to go in several times with a remainder of 6. And that 6, as a letter, is G. That was the original plain text. So finding multiplicative inverses, it turns out, is the key toward, literally, the key towards decrypting many ciphers. It's starting with the affine cipher, but also very much involved with some of the more modern ciphers we see. So finding multiplicative inverses of integers mod other integers is important, and we do it by the simple Euclidean algorithm and extended Euclidean algorithm. Thanks for watching.